that I'm giving, I want to talk about the properties of dark matter halos. And the reason for this is quite straightforward, and that is that if our structure formation paradigm is correct, then dark matter halos are in fact the basic structural unit of the present universe. Because, well, as we'll see, almost all dark matter is part of some nonlinear object, which we call a halo for lack of any other name. And the baryonic part that we see, the stars and the gas, are heavily influenced by these dark halos. In particular, galaxies form at the center of them. So the kind of issues one might want to know the answer to are whether all dark matter is part of some halo or not today. Was this always the case? How far back in time do we have to go for the universe to be smooth on all scales in the dark matter? How far back do we have to go before we no longer have to worry about nonlinear effects? What is the typical mode by which these halos grow? Do they collapse in a single unit? Do they gradually accrete, like a black hole perhaps accreting mass at the center of a galaxy? Do they grow by merging? What is their spatial distribution? What is their structure? You can think of the structure, I mean their internal structure, so what is their density profile? Are they spherical? If not, how far from spherical are they? What about all the substructure that forms within them? How is it distributed? How much of it is in very small objects? How does it evolve with time? How does it depend on position inside, for example, the dark halo of our own galaxy? And then in the last lecture, I'll also talk about other structures which can form in the dark matter, which are the equivalent of light caustics, or if you like, rather like tidal tails forming in interacting galaxies, whether these may be of significance. And the reason these may be of significance is because they've been claimed that they could affect our ability to detect dark matter directly. Because in the end, if we're going to confirm the dark matter paradigm, we have to find some way to detect dark matter other than by its gravitational effects. I think only then will we be really convinced that this is the true solution, rather than, for example, a modified theory of gravity. Another aspect of trying to specify the properties of the dark matter distribution is because some aspects of them can be well measured, we can then use them to test our picture for how structure has grown. But we can only do this provided we understand their properties well enough. And then the final point here, which is an important one, which I won't get to in these 3 lectures, is how the dark halos affect the baryonic material that we see, how they cause the galaxies to form, how they influence the properties of the galaxies. And then there's a reaction in the other direction. The formation of the galaxies does change the structure of the dark halos that they are embedded in. That is also important, but I won't get to do more than make a few remarks about it. So here are images of two dark matter halos from a couple of simulations, quite old simulations now. The one on the left is supposed to be the dark matter halo of a galaxy cluster, and the scale bar you see is 1 megaparsec long. The one on the right is supposed to be the dark matter halo of something like the Milky Way, and the scale bar there is 100 kiloparsecs long. So you can see the scale of the two images differs by a factor of 10 in linear scale, and the mass of these two objects differs by a factor of 1,000. So you can see that with this scaling, they actually look quite similar, except because of the different epochs when they were made, different color schemes were used. So you can see there are patterns in color schemes, the ones that become popular, change every few years. So you can see several things. You will see they're very centrally concentrated. You can see they're not round. and you can see a very large amount of internal structure inside them. So let me show you a movie of how one like the one on the right here, this Milky Way halo, how this may have formed. Okay, this shows up. So what do you see here? This is a scale bar. This is in co-moving units. So this is at a redshift of 50, close enough. So this is actually only 10 kiloparsecs in physical units long. This is because this is a co-moving scale. This is a distribution of dark matter at redshift of 45. So this is only 60 million years after the Big Bang. And this is the dark matter distribution. And when I play it, you'll see it's rotating. The rotation is not real. That's just to help you visualize the three-dimensional structure. So as the object starts to form. So you can see there's already some nonlinear structure here, redshift 35. We stop it at redshift 20 when we get there. So this is what the dark matter distribution of our own Milky Way is supposed to look like at a redshift of 20. All the material here will end up as part of the Milky Way. The biggest lumps that you see, these things, have a mass of about 10 to the 8 solar masses. So that means they have about 10 to the 7 solar masses of baryons. These objects, the baryonic material here, if it was included, would be able to cool. You could imagine it was already making stars. So this object, you could think of all the massive things in this picture, could already be making stars here at a redshift of 20. So redshift of 15, the most massive objects now are about 10 to the 9 solar masses. Stop it again at redshift 10. So here at redshift 10, this is supposed to be the middle of reionization. I think Wayne would probably agree this is now more likely than the higher values he had this morning from his earlier models. So these things all have masses now of 10 to the 10 solar masses. So that's big enough to hold quite a large dwarf galaxy. So this thing, as I said, all this stuff is going to be part of the Milky Way's halo. These individual objects could already have quite sizable dwarf galaxies inside them, maybe powering the reionization. So what you'll see now as we come down towards redshift 6 or so, these are now the redshifts where we actually can see something in the real universe. You can see all these things are actually going to fall together. You can see quite a lot of complicated dynamics here. You can see individual objects orbiting backwards and forwards inside the main system. But after about redshift 5, there was always one dominant system here. And all these other things are just flying around. If you follow carefully, you can follow individual objects going in and out around the center 5 or 6 times. Here we're now almost down to redshift 1. So this is, according to the model, which we're encouraged to believe is supposed to be our standard paradigm, is what the dark matter around our Milky Way should look like at the redshifts of the galaxies we actually observe in the real universe. So you can see there's a very well-defined central concentration here, but there's a whole host of small things falling around, orbiting, and occasionally still falling through the center. So not much happens here, so let me stop there. So how can we understand this? How can we make a structure of this? So what I want to do now, and for most of the rest of today, is go through simple models which allow us to treat this buildup of structure. And the problem is this was a very large simulation you just saw. Nevertheless, the smallest object which you could see or could be simulated in this particular calculation I showed you had a mass which was about 100,000 solar masses. But we believe if the cold dark matter was a WIMP, a neutralino of the kind that Chang Pei was talking about this morning, that it's very likely the smallest objects that could form would have a mass about the Earth's mass, or maybe even smaller. So that's still another 12 or so orders of magnitude below anything you could see in the simulation. So in the simulation, you could see from the mass of the whole system, 10 to the 12, down to maybe 10 to the 5. So that's 7 orders of magnitude. There's still at least another 12 orders of magnitude to go. So we would like to be able to understand things well enough to extrapolate the rest of the way. So the kind of simple model I want to go through here is a way of trying to understand qualitatively, and perhaps quantitatively, how such objects build up over the full range. So what I want to go through is what's called the extended Projector model for structure growth. And this is based on the linear theory which Chang-Pei went through with some small additions. So we start with this quantity, which is what we call the overdensity. So it's the density above the mean measured in units of the mean density. Okay, so there's the overdensity at a position x expanding with the universe at redshift z. So in linear theory, as Chang-Pei said, all fluctuations grow at the same rate, which means that all that happens is structure amplifies with time. So this function, in linear theory, function of position and time, actually factorizes into a function of position and a function of time. So let's normalize this fraction of time. So it's 1 at the present day, at redshift 0. Then this is the linear density field extrapolated to the present day universe. And we can Fourier analyze this, as both Chang-Pei and Wayne were talking about. So this would then be the Fourier amplitude of this particular wave number, and this is just the definition in my Fourier transform here. Okay, so that's the linear density field. This is how the linear structure grows, and this growth factor increases in the dust universe in proportion to the expansion factor at early times, and then slows down below redshift 1 because of dark energy. So that's this. So now, the goal of this exercise is to ask what, for each particle in the universe, at each redshift, what size object is it part of? And the trick is to consider a scale. So you introduce a scale in this problem by smoothing this density field. And the smoothing is done in the simplest possible way, just by throwing away all wave numbers above some critical value. So we introduce this smoothing wave number, Kc, and we restrict the Fourier integral here to only the smallest wave numbers, and so the longest waves. So this then smooths the distribution by throwing away all the high-frequency waves. And so as you vary Kc, you vary the smoothing. So if Kc, this critical number, is very small, that corresponds to a very large wavelength, you've only kept the longest waves here, and you have a very smooth distribution. If you make Kc larger, you've added more waves, and you have more structure in the linear distribution. And then to define some notation here, let's take the RMS value of this smooth field, averaged over x, to be this variance. And so this smooth field increases in time. Its variance increases in time as the square of the growth factor, and there's this variance as a function of scale. So that's the typical scale on which you smooth. And so then you can relate that to a mass. The wave number is 1 over a length. So actually, if you make the filter corresponding to this sharp cutoff, this is the mass enclosed by that filter. This is a characteristic mass scale associated with this cutoff. So let's imagine what happens. So now let's go to a particular position and ask what happens. So as you start with Kc small, so very large wavelength, a very high smoothing, and you increase it all the way to infinity, so you can put the whole information in, the mass decreases from a very large value to 0. And the value of the density you get at any particular point will execute some kind of random walk. It will fluctuate as you add more and more waves in. And the reason for choosing this particular kind of fluctuation, and a critical point about this is that as you increase the smoothing, what happens is you just add in new waves that you didn't have before. But the ones you already have are not changed. You can see below Kc, these two things are here. So I change Kc, all I do is add in new waves. Now, if you have a Gaussian linear density field, as Chang-Pei told us, then the power spectrum contains all the information. And one of the consequences of that means that the phases of the waves of the different components are uncorrelated with each other. So this means that when you add in, when you change Kc, you change the value of this, so you change the value of the smooth field. The change is only due to the new waves you've added in. They're uncorrelated with the ones you had before. So the change that you make is independent of where you were, of the value you had. So this is a random walk, which is called a Markov random walk. So at each point, you make a step. The size of the step doesn't depend on the value at the position where you were at that time. So this is the critical point why this gives a simple result. We have a Markov random walk. So let me get now to how this allows you to make a model for structure. So what we know is if you take the simplest possible model for a perturbation, you have a uniform universe, you take a spherical region, and you make the density in that spherical region slightly higher than the average, then what happens as this very simple system expands is the linear density gradually increases and increases. And in linear theory, it would just keep increasing in proportion to that function d that I gave you. But in the nonlinear case, what happens is your spherical region acts like a little independent universe. And so if it's sufficiently dense, it will actually expand, reach a maximum size, and recollapse to itself. And so you can ask yourself, at the time when it recollapses, that's the time when it makes a nonlinear bound quasi-equilibrium object. So we can ask, at that time, what density does linear theory say it should have? And the answer is, and almost independently of the cosmology you're in, when the linear overdensity is predicted to be 1.7, that's the time when this object collapses. So this allows us, in linear theory, to identify a time of formation. It's the time when linear theory says you reach an amplitude of 1.7. That's the time when you actually collapse and come to equilibrium. So the critical assumption in this whole game is that if you focus on a particular element and look at its random walk, you can ask, if I have a very big smoothing, the overdensity on that scale is very small. It's predicted to be much less than 1.7. If I have a very small smoothing, in some regions at least, I'll have a very large predicted overdensity. It'll be part of some object, much bigger than 1.7. So as I gradually increase the smoothing mass, or decrease Kc, I can ask what's the largest mass, or the smallest value of Kc, where I'm still above 1.7. And say that's the object that this particular mass element belongs to. So the assumption is that at some particular redshift, the mass element which was initially at some position is part of a collapsed object, and that object is the one which has the largest mass for which the linear overdensity with this particular smoothing is greater than this critical value. And this is known in random processes as an upcrossing problem. So you have a random walk, and you ask when does a random walk, as we gradually increase Kc, this executes a random walk, when does it first cross this value? And when you cross it, that's what determines the value m, which is supposed to be the value the thing is part of at that time. So this you have to sort of take on faith and then test. This is the ansatz, or the hypothesis behind the model. Once you make this, then you can calculate many things you're interested in. So for example, just from the property of Markov random walks, you can find the fraction of all random walks, or fraction of points, whose first upcrossing below Kc is below a particular value, and that's the fraction of the mass in collapsed objects which are bigger than this. So you can find the fraction of all the cosmic mass in objects with a mass above some value. So you go through this, you can derive immediately the mass function, the number of objects as a function of their mass and redshift. And the answer is this famous Press and Schechter formula. And in fact, doing the argument this way, you also get rid of the famous factor of 2, which was missing in the original Press-Schechter derivation, where they used a slightly simpler argument. And so what you see is the mass function. So this is the redshift, remember, comes in only in d, and the mass comes only in sigma. So large mass means small sigma. So as the mass becomes large, sigma becomes small, you get an exponential cutoff here. And this is roughly a power law behavior on small scales. Okay, so let me give you an example of how this works. So here, and you see this plot a number of times, so this is a plot of such a random walk. The vertical axis here is the overdensity of a particular point with different smoothings. So this is the overdensity, and this is the smoothing, and it's measured by the variance on the scale, the smoothing scale. Okay, sigma. So the variance increases this way. So the variance goes up, that means the smoothing is going down. So the variance increases this way, that means the spatial scale of the smoothing is increasing this way, and the mass of the smoothing is increasing this way. So when you smooth very heavily, you only include very small k's, that's the first part of the walk. As you smooth less and less, you include more and more waves, more and more k, the variance goes up, and you move along the walk in this way. And then what's shown here is the overdensity with the growth factor taken out. So then it's independent of time. And this is such a random walk. So when you're at a particular point, let's say you're here, and you move to here, then you increase your variance, you get some additional variance, you have to make a step. The step you make is independent of whether you are here or somewhere else. So you can see two different walks here, corresponding to two different particles. And they're identical up to this point, and then they were independent. And in fact, if you look, A is just the mirror image of B about this point. So in fact, at every point after, so on the left of this point, the two are the same. On the right of this point, every time A goes up, B goes down, and vice versa, by the same amount. So that means A and B have to be equally likely, because the random walk is just as likely to go up as to go down. So these are equally plausible random walks, they're just two different ones. So this represents two different particles. So let's ask now, what's going to happen with time to these objects? So what happens with time is D gets bigger. Remember, D is the growth factor. So it's very small in the early universe, and it's 1 today. So D increases with time. So in very early times, D is very small. So 1.69 corresponds to somewhere way off the top of this plot. As we go on, D gradually increases, and then 1.69 over D will become on this plot. So what happens is our threshold we have to cross with time gradually comes down. So let's go to an initial time, tau 1. So now 1.69 over D is here, say. So this random walk, you can see A crosses at this point. So this point corresponds to some variance here, which corresponds to some mass. So at this rather early time, tau 1, A is supposed to be part of an object of this mass. B hasn't crossed it here, so maybe it crosses it over there somewhere. So either B crosses over here somewhere as part of a very small halo, or it doesn't cross at all, and then it's not part of anything. Okay? Okay, let's go a bit further forward in time. D will increase, so the barrier will come down. Come to a second time here. So what's happened? Well, A moved from there down to here. So you can see the variance, it moves slightly to the left. So that means this object has just grown by accreting material. It's grown in a smooth way, gradually moving to the left, so towards larger masses. So A has grown slightly by accretion. B is now part of something over here. So it's either collapsed for the first time, or maybe it merged into something bigger, but now it's part of something which is on the plot. If we keep going forwards in time, here we are, time 3. You see A has increased a little bit further. B has now jumped from here to here, and B is now more massive than A. Because at this point, suddenly, B jumped from here to here. So this particle's object fell into some much bigger thing. So this is how this allows you to track mergers. So it means here it was in as part of a small object, now it's part of a much bigger object, it must have fallen into a bigger object. If we go later, now we're past the point where these two diverge, so now in the future these two halos are going to have the same history, future history. But if you look at this point, ask what's here, you look on this region, on this scale, you can see the overdensity is large and positive. So on this smoothing scale, these two halos are part of an overdense region. On this larger scale, Y, See, this is further to the left, so this corresponds to a larger region. It's actually below 0. So the two halos are part of an underdense region. This also shows you how you can use the same formalism to talk about the environments on larger scale of the objects. So this is how you can talk about their clustering. So there are a number of consequences from this model. So this is just a model, okay? So one thing which is quite striking is because this is a random walk is Markov, it's reconstructed down here, the assembly history of a halo, that's how it was put together in the past, is independent of its future. So let's take, we have two halos here, right? This is the point where they diverged. They have different pasts. But these random walks to the right don't depend on what happens on the left because the process is Markov. It only depends on the fact that you cross at this point. So this means that what happens on the right here doesn't depend on whether we have the particular random walk you see here, or you have one which went like this, or you have one which went like this. They're all equally likely because this side doesn't depend on this side. So this means the way the halo is assembled doesn't depend on its future. And in particular, then, it doesn't depend on whether you happen to be high or low here or here. So it doesn't depend on its environment. So this model predicts that the way things are put together doesn't depend on what's going to happen to them in the future, whether they're in high or low density regions. Another nice thing is, if you ask the problem, let's say we take an object and we know its mass at a given redshift. Let's say we take the objects here. They have a particular mass and correspond to a particular redshift at this threshold. So we have two different objects here. And now I want to ask, so we take the different mass elements which are part of those objects at this time and ask where were they at earlier times. That depends only on the random walk to the right. So if you look at this problem, because these steps to the right are independent of the rest, what happens to the right is exactly the same problems we started off with, just with the origin shifted to this point. So this means you can solve the problem of what happens of solving for the progenitors of a halo of given mass and redshift. That's the same formula I had before. All you have to do is shift the origin to this point, and the same formula works. So that means we now have formulae which tell us, for a given object, what all its progenitors were at some earlier redshift. And those things can then be manipulated through the calculus of probabilities to give you things the other way around. We have things of a given mass at high redshift. What are they going to turn into at redshift 0? And then the same kinds of arguments allow us to calculate the bias of clustering, because they say if we know on a particular scale we're in an overdense region, so on this particular scale we're in this overdense region, what's the probability of having a halo of this mass? You just have to do the random walk starting at this point. If we were in a low density region on this scale, we'd have to do our random walk starting at this point and ask what's the probability of crossing. So then we can ask, in high and low density regions of the universe, how does the mass function change? This is a way you can calculate the clustering. Okay, now I hope that's clear enough to explain how this works. Now the question is does it in fact describe reality? So you can take a simulation. In the simulation, we know the linear initial conditions because we put them in when we started the simulation. We know the final outcome because we calculated it. So every particle in the simulation, you can just reconstruct its Markov random walk, ask when it crosses a threshold, see what mass object should be predicted to be at the present day. Then you did the simulation, so you know the answer. So you can plot one against the other, and this is what you get. So this is the mass of the halo in which the particles actually found when you run the simulation, and this is the mass where it's predicted by this random walk. And well, it's not perfect. I think you can see there is definitely a clustering along the diagonal line. Of course, if it was perfect, they would all lie exactly on this diagonal line. So part of it is because we're getting to the resolution limit. This is actually one particle down here. So we should probably only look at this part of the diagram where the simulation has resolved it fairly well. But even up here, there's lots of scatter. So clearly, it's quite approximate. Does it work statistically? Rather than asking whether it gives the right answer for every single particle, we can ask, does it give you the right mass function? Then things don't look so bad. here are results on the mass function. So this is the number of objects of a given mass as a function of that mass. Here's the mass. We're going from 10 to the 8 solar masses to 10 to the 16 solar masses, so we have 8 orders of magnitude on the axis here. This is the abundance. With very large simulations, you can get these things with quite small error bars. This is the simplest thing to do, of course, with simulations, is just find all the objects and count them. And there are 2 simulations here. One is the Millennium simulation, which was finished 2005. And this is the second simulation with the same number of particles, but 100 times better resolution, which is Mike Boyle and Colchin's working on at the moment. And this is just putting the 2 together. So you can see you get mass functions with very low error bars at redshift 0, 2, and 6 here. The simple formula I just went through gives you the dotted curves. So it's not great. It's off by a factor of 2 in here. And you can see that it's systematically off at high mass n. You can play around with these kinds of formulae, change the shape of the barrier, or just fit the numerics and get better fitting formulae which have the same dependence on the variables, but they're slightly different functional forms, and get things which fit much better. So this is these were from a paper by Warren, where they were fitting their own numerical data. They fit these numerical data very well. What that tells us is that different people do the simulations, they get the same answer. So bear in mind that the simple formulae here are not good to a factor of 2. Nevertheless, you can find out quite a lot of interesting things. So let me start going through some plots. I'm going to show you a number of these plots. So let me explain what's plotted. So this is the number of objects per unit volume. So rich clusters are about 1 per million cubic megaparsecs. They're about 10 to the minus 6 here. Things like the Milky Way is 1 for every 100 cubic megaparsecs about here. This is redshift from 0 to 20. And so here's a curve marked 10 to the 12. So this shows you, at this point, redshift 0, the abundance of halos of 10 to the 12 solar masses is about equal to the abundance of the Milky Way galaxies the brightest of the Milky Way. That's lucky, but well, it's not lucky. We set it up that way, right? That's how we chose the formula. The abundance of things of 10 to the 15 solar masses, 10 to the minus 6. That's where the rich clusters are. Things of 10 to the 7 solar masses are about 4 orders of magnitude more abundant than the Milky Way's halo. Now look how these things evolve with redshift. And some of these things may look surprising. If you look at the rich clusters, you go to redshift 1, and they've already dropped by 2 orders of magnitude. This is why people use the cluster abundance to measure cosmological properties. They're predicted to depend very strongly on redshift, and this drop-off depends on the growth factor over this interval. And so it will depend on whether we have dark energy or not, on which kind of dark energy we have. If you take Milky Ways, actually from 0 to 3 barely changes. So you can't do the same test using Milky Way halos. It won't work. If you go to 10 to the 7 solar mass halos, there's almost no change out to redshift 20 in their abundance. So that's summarized here. Rapid abundance drop for the rich clusters. Milky Ways, 10 to the 12, they drop by less than an order of magnitude all the way back to redshift 5, so most of the region where we see real galaxies. And 10 to the 9 solar mass halos, they're almost constant out to redshift 10. Now, if you know an object has a given mass and it collapsed at a given redshift, you know what its mean density is, you can work out what its temperature is. So this is the plot with only the mass. If you look here, the red dashed lines are the same lines as before. So here's 10 to 8 solar masses, 10 to the 10 solar masses, 10 to the 12 solar masses, 10 to the 14 solar masses. So those are the same curves you had before. The black curves are now the temperature that's expected in the halo, just given by the virial theorem. So you can imagine if you put a gas atmosphere in hydrostatic equilibrium inside the object, it's the temperature it would have. So it's the characteristic temperature. Of course, the dark matter itself doesn't have a temperature in the same sense. Yeah, it would be if you put a gas in static equilibrium inside one of these halos, it's the temperature it would have. So it's a characteristic temperature in that sense. So for example, Milky Way halo, that was 10 to the 12. 10 to the 12 is this one. here, you can see that's about just under 10 to the 6 degrees. That's the characteristic temperature of gas in the halo of the Milky Way. Down here, 10 to the 6, that's a few times 10 to the 7 degrees. That's a few kilovolts. That's the temperature of the gas in a rich cluster. And so you get back all the numbers you know and love when you look at these things. What's quite interesting is to look at how they vary with redshift. So temperature increases with both mass and redshift. It scales in this way. So if you look at, instead of at massive clusters, at hot clusters, ones that emit in the X-rays, so let's say temperature above a kilovolt, 10 to the 7 degrees K. Where's 10 to the 7? Here it is. It's this curve. See, it's flat all the way from 0 to 3. So the abundance of hot clusters, which you would emit in X-rays, is almost as high at redshift 3 as at redshift 0. So although the abundance of clusters by mass drops like a rock, the abundance of clusters by temperature is not changing nearly as much. So you have to be very careful, because the temperature may be what determines whether the X-rays actually find the clusters. Take 10 to the 6, roughly like the Milky Way. That's this temperature. You can see you go all the way back to redshift 6. There are just as many as there are at redshift 0. So these are things like galaxies with X-ray temperatures corresponding to galaxies. Over the whole range where we see galaxies, the temperature, the abundance doesn't change much. You take 10 to the 7.5, that's this curve, I guess. I'm lost. Here's 10 to the 4 degrees. So gas above 10 to the 4 degrees, the hydrogen is collisionally ionized and it can cool rapidly. So you expect cooling to be efficient in anything which lies above this 10 to the 4 degree line here. So you can see 10 to the 7, 10 to the 8 here, 10 to the 8 solar mass halos can cool down to redshift 7. So all those things that you saw in the simulation of the Milky Way, which are above this temperature and those redshifts, those could all cool. That's why I said at the time they should be making stars. In fact, 10 to the 7.5, you can cool at redshift 20. So at redshift 20, there were, in the Milky Way simulation I showed you, quite a few objects with masses above 10 to the 7.5. Those should have been able to cool through hydrogen line emission. This is not a simulation, right? This is, yeah, but anyway.
The analysis applies to the dark matter, right? But then you're talking about...
Right, but the real universe has gas. So in the real universe, when something collapses, it will have its 15% gas. That gas will shock to a temperature which corresponds to these values. So these are the characteristic temperatures that the gas will have inside these dark matter objects. So what I'm saying is the gas associated with those dark matter lumps you saw in my simulation of the Milky Way would have had a temperature at those redshifts above the collisional ionization temperature for hydrogen, so that gas will be able to cool.
But the barium gas is not going to be in equilibrium with the dark matter gas.
Yes, it clusters with it. That's what Chang Pei showed us. Remember, once there's no longer coupled to the photons, then the dark matter, the baryons follow the dark matter. And that happens until some other astrophysical process, like new ionization or galactic wind, some other process separates them again. So when these things are collapsing, they will have cold gas with them. That will shock when the things collapse, and the temperature it reaches after the shocks will be of the order given by this plot. And so this plot then tells you whether it will be able to cool and perhaps form stars. It's telling you something about the abundance of objects. Here we have redshift again. These are the mass. This is telling you what fraction of all the mass in the universe is in the particular object. So the way you read this is, here's the Milky Way, 10 to the 12 is here. Today, about 30% of all mass in the universe, dark matter, is in objects with mass larger than the mass of the Milky Way. If you take the rich clusters down here, 10 to the 15 was here, about 1% of all the dark matter in the universe, this is 0.01 on this curve. Today, about 1% of all the dark matter is in objects with the masses as 10 to the 15 solar masses or more. Okay. And if you look at the universe today, you can see half the mass is predicted to be down here at this level, which is about 10 to the 10. So today, roughly half of all the dark matter is predicted to be in objects with mass above 10 to the 10 solar masses by this. Now what you can see is you go back in time, these numbers all drop dramatically, right? Because these all go up high. So half of all mass is in objects above 10 to the 10 solar masses at redshift 0. If I go back to redshift 5, it's crossing the 1/10th line here. So only 10% of the mass is in objects above 10 to the 10. If it crosses the 1% curve here, following 10 to the 9, sorry, 10 to the 10, crosses the 1% here, it's about redshift 9. Go to redshift 20, it's below 1 part in a million. So almost no mass is in such massive objects. I already said that more than 1% of the mass is in things above 10 to the 15 solar mass at redshift 0. If you ask that a photoionization temperature was about here. So at redshift 0, 40% of all the mass is in things where the characteristic temperature is below the photoionization temperature for hydrogen. So since the universe is currently ionized, what that means is the gas won't be able to fall into those halos at all, because the gas has been ionized by something else. That's exactly the effect I was talking about. The other astrophysics has stopped the gas being able to fall into such small objects.
Excuse me, how well do these results of this plot fit with the data?
What data? What data?
I mean, is there data to...
I'm going through physics. There is data as well. And the virial theorem is physics, right? This is all this. The part which is uncertain here is the calculation of the abundances, right? That based on this Projector theory. So that you have to check with the simulations. And that I showed you, the check works reasonably well, but certainly not perfectly. But all these things are then just consequences of that from physics.
Another question, how much is the influence of assuming lambda cold dark matter, in particular the dark energy? I mean, the results change.
Yeah, they change quite significantly, but depends how big a difference you care about. So different things change differently. There's a paper by Wang et al. In 2006, which this is all WMAP1 cosmology, which went through the same, makes the same plots for WMAP3, so you can at least see what happens for that range of parameters. I mean, these things are all, it's easy to make these plots, but the reason I go through this is because I find them very useful just thinking roughly about what's plausible inside the model, because you just go to the plot, you can go to a particular redshift, you can see the abundance, the temperature, how clustered things should be, and so on, and get some idea of what you should expect. So this is a part that uses the clustering part of the theory that I told you, the fact that you can predict how strongly clustered the object should be. So what's these lines, so the red curves are still the mass curves as before, 10 to the 10, 10 to the 12, 10 to the 14. And this is the RMS fluctuation in a sphere of 8 megaparsecs. This is the standard measure often used in large-scale structure for the amplitude of clustering. You take a sphere of co-moving radius 8 megaparsecs, and you move it around inside the universe, and you ask, what's the fluctuation in the density of your population inside this sphere? That's a measure of clustering strength. It's just a conventional measure. And this is that measure for halos of different kinds. So look at redshift 0 here. Here's the Milky Way's halo, and the clustering strength here is 0.8. So halos of mass of the Milky Way's halo today are slightly less clustered than bright galaxies. Bright galaxies have a value of 1 for this quantity. Interestingly enough, though, as you go back in time, all the way back to redshift 6 or 7, it doesn't change. So you take halos of that mass, they're just as clustered at redshift 7 as they are at redshift 0. So that's, in fact, if you take slightly somewhere here, you can see you can all go back to redshift 20 and it doesn't really change. So if you identify the clusters by their mass, you get this rather paradoxical result. The clustering doesn't change with time, even though obviously structure is growing dramatically in the universe. Here's the same thing now, asking not where is the stuff at the time you look at it, but where is it today? So we want to ask, let's say we formed stars in 10 to the 9 solar mass objects, or no, 10 to the 10 solar mass objects at redshift of 10. You'd be here, 10 to the 10. Here's redshift 10. You'd be there at this point. You'd be on this curve, which is 1.4. The remnants of those objects today would have a clustering strength of 1.4, which means they'd be substantially more clustered today than bright galaxies. So that means the remnants of those early objects should be in the most strongly clustered populations today. In fact, the remnants of any object at redshift 2 that had an abundance similar to the present-day galaxies, or to the galaxies in most high redshift surveys, they'll be more strongly clustered than bright galaxies are today, because all these curves, then you can see here's 1. So this is what corresponds to strongly clustered galaxy, to bright galaxy clustering today. These are all, it's way up here. So all these points, which correspond to moderately abundant objects at high redshift, they're all far below that. Okay, here's another test of this model. So I told you the model predicts the clustering, the environment of an object doesn't depend on how it was assembled. It only depends on its mass. If you know its mass and its redshift, then its clustering should be specified. So here's all the halos above 10 to the 11 solar masses in a thin slice through the Millennium simulation, except it's not all of them, it's only 1/5. And in particular, I've taken the 5th, which were assembled most recently. That's the distribution. Now I can take the opposite end of the distribution, the 5th, so the same mass, but the 5th that was assembled at the earliest times. And that's the distribution. So I think you can agree they're not clustered in the same way. So this means that this simple consequence of the Markov random walk does not hold. The clustering depends on something else besides just the mass of the halos. So that's shown here. Here's what's known as a bias. It's a measure of the, if you like, of this quantity sigma 8 in units at the present day. And this is now for all the objects of the same mass, but these are the 10% latest forming. These are the 10% earliest forming, and this is just the 10% parts of the distribution. And you can see the clustering bias, or the clustering amplitude, goes from 0.45 here to 1.2 here. So it's a factor of 3 in B, which is a factor of 9 in the power spectrum. So it's not a small effect. You can plot the strength of this effect as a function of the mass of the object, and it turns out this effect is strongest for the smallest objects. So there's now the mass of the halos plotted here. So Milky Way's halo would be here somewhere. So these would be the halos of small galaxies. These would be rich cluster halos. This is if you just take all the halos regardless of when they formed. This is if you take the 20% earliest forming and the 20% latest forming. So this is the big difference I was showing you in the plot. And you can see as you go to more and more massive objects, it gets weaker. So this is what the first pointed out. It turns out, though, it depends on which property you look at. So this is the same thing, just shown in a different way. This is the bias again. This is now a function of the mass, except it's the threshold. It's the threshold which I used in the Projector theory, which is a function of the mass and redshift. It turns out that if you use this variable, then all these things line up on top of each other at different redshifts. So you can stack data. So this is if you don't separate by formation time. These are the 20% earliest forming, 20% latest forming. That's how it splits by formation time. Let's fit it by how concentrated the halos are, what the radial distribution of the dark matter is. So this, again, the symbols are the same as they were before, but now these are the ones that are high density, very concentrated dark matter halos, and these are the low density ones. So you can see at low masses, the high concentration ones are the most clustered, and at high masses, the low concentration ones are the most clustered, and it crosses in the middle. So the two things don't match. Here's what happens if you take a measure of how much substructure they have. Doesn't matter much what it is. These are the ones with relatively little substructure. These ones with a lot of substructure. The effect is roughly similar at all masses. Here's a different measure of substructure, and it looks different. So it even depends on which measure of substructure you use. Here's what happens if you take how rapidly they are rotating. Again, you get an effect which is roughly the same. So the ones that are rotating rapidly are more clustered than the ones that are rotating slowly. It's the opposite way around for galaxies, right? The ones that are heavily clustered are the ellipticals, which are slowly rotating, and the spirals, which are rapidly rotating, are less clustered. In the dark halos, it's the other way around. And again, it's roughly constant. So the conclusions from this part, which looks like as far as I get today, so this is good because now my 2 lectures are already stretched to 3. So the large-scale bias of the halo clustering relative to the dark matter. So the bias is measured relative to the dark matter. Right? So all these things I'm saying, it's more strongly clustered, less strongly clustered. That was relative to how strongly clustered the dark matter was. So it depends on halo mass through this combination. That's why the curves of different colors, which correspond to different redshifts and different masses, lay on top of each other. And it depends on formation time, concentration, substructure content, and spin. But it depends on each of these quantities in a different way from each other. So you can't relate one of these dependencies in any simple way to the others. So what this means is the clustering, if you look at it, if you worry about the clustering strength with this level of accuracy, all these things become important. And it seems that all these things should have some influence on the kinds of galaxies that form inside a halo. So therefore, it would be surprising if some aspects of this dependence weren't reflected in the properties of the galaxies. Although then you would need to understand how to relate the galaxies to the halos more accurately in order to put that together. And I guess that's going to be enough for today.